So, good question is the difference between something that's chiral or achiral and this term enantiomers. Alright, so the big difference is chiral or achiral refers to one molecule, right? To one molecule or thing, right? Like this molecule is chiral, this molecule is achiral. Enantiomer refers to the relationship between two molecules versus one. Two molecules that are mirror images of each other. Mirror images of each other. Right? One molecule is not an enantiomer. Is it an enantiomer of something else? Right? It's a relationship between two things. Right? Like my two hands, my right hand and my left hand are enantiomers of each other. My right hand by itself is chiral. My left hand by itself is chiral. So enantiomers refers to things as a pair. Same with diastereomers. We're talking about the relationship between two things. All right, so chiral and achiral is referring to just one molecule. One molecule is chiral or achiral. All right, let's make up kind of a difficult priority ranking one. So we did a good one in class in the clicker questions with esters, right? With the acetyl bondos, the carbonyls, and the triols, and all the ethers, right? These terms you should know, right? I'm not going to draw what an ester is. Google it, right? Or an ether. But let's see what I can come up with here. It's going to have to be sp3 hybridized. It's going to have 4 different things on it. How about that? And I'll wait to take it a step further. I'll add wedges and hatches in a second. Maybe we'll decide we want to make it R or S. But first, we're just going to prioritize this. Right? So, first step to prioritize this, we go out 1 carbon each, right? We start here in the middle. This is the asymmetric center, right? This is the carbon that has 4 different things bonded to it. So we go to carbon, to carbon, to carbon, to carbon. So at this point, there's no difference, right? Everybody's tied. Right? We've got carbon, 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 carbon. No difference. So we go out 1 more carbon. So here we go to a carbon, okay? Carbon, carbon. Oh, maybe I should back up a second. Carbon, 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 carbon. All right? This carbon is bonded to what? 2 hydrogens and a carbon. So its best play is a 1 carbon. This carbon's best play is just 1 carbon at a time. Carbon. This carbon's best play is a carbon. This carbon's best play is a carbon. Okay. This carbon's next best play is a hydrogen. This guy's next best play is a carbon. This guy's next best play is a hydrogen. And this guy's next best play is a carbon again, right? Because this carbon is bonded twice to this carbon. So we know at this point, this piece and this piece are lower ranked than these two, right? Everybody sees that? I mean, you start to get good at this and look at it faster and say, well, this carbon is bonded to 1 carbon, this is bonded to 2. I know this is ahead, right? You can get a little faster. But so now we're down to this one versus this one for top priority, right? I think it's easiest to find the top priority one first. Okay? So we're back here. Carbon, 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 right? Last play is a carbon H. Last place is carbon H, right? We're still tied. So we move on out. This carbon right here is bonded to 3 hydrogens, right? So its best place in H. Now this carbon is a little different. What is this carbon bonded to? It's certainly bonded to 2 hydrogens, but what else is it bonded to? The carbon back. So this has higher priority. So when you have a pi bond like this, right, this guy has to go back. You count that carbon going back, that it's still bonded to a carbon when it has a pi bond like that. Yeah. Right? Because technically, the other way you can look at it, right, this carbon has 3 C, this has 3 H's, this one has 2. This one has top priority. So that means this would be 1 or red, right? And I know I do the red, white, and blue thing. You don't have to do it that way, but I will do it that way. But you don't have to follow that rule if you don't want to. If you read the book and you like that somehow, by God, go for it. You can read that, whatever that is, go for it. But that's red. That's 1. We're all there. So that means this other one has to be 2, which of course is white. Right? So now we're down to these last 2 things. So we've gotten to carbon, 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 carbon. This carbon and this carbon. This carbon's best play is a bromine, right? This carbon's best play is another carbon. Who wins? Bromine. So this would be blue and red, right? And this would be green. So notice a couple things, right? This is the longest chain, and it has the highest atomic number thing, but yet it's the lowest priority, right? Longest chain with the iodide, lowest priority, because we go how many bonds at a time? Just 1 bond at a time, right? So that's why I purposely did that. Okay. Okay with the rankings? Kind of get to that harder question. So what do we want? Let's just make this RS. Which one do you guys want to make it? RS. We'll make this S for the sinister nature of ourselves. S. So we got to take out our molecules, our R and S molecules, and we'll figure out how to do this. So at this point, you should have grabbed the S molecule, and at this point, it doesn't matter what's wedged and what's hatched, as long as it matches what that molecule is, right? One thing that does matter is the wedge and hatched pieces have to be next to each other. You can't have this guy, the white one here, be wedged and the red one be hatched. You can't have this bisecting it. That's one thing. The wedge and the hatch have to be on the same side. They have to be next to each other. But multiple things can be wedged and hatched. It doesn't matter. So there's a couple different ways we could do this. There's 4 ways to do this. So how do we want to do it? What do you guys give me a suggestion? Which one do you want me to make? Which one do you want me to make wedged?
The green.
The white.
Perfect. We have a debate. All right. So we'll make the green wedged. So if the green's wedged, we either have to use, right, if the green is wedged, we either have to go with the white or the red, right, being hatched. So which one are we going to make hatched, the white or the red?
Red.
Does it matter? I think it does matter. Which one are you going to make hatched? The
Red.
Well, I'm willing to go through the thought experiment. Let's make this one hatched. Let's take a step back and now let's see if this is right. So following much discussion, right? This is indeed an S conformation, right? S or stereoisomer. We also could have made the wedge on the white and still had the S too. It's just rotate the molecule a little bit, but it still would have been fine. So there's a couple ways you could have done this, right? Good. All right, let's look. Between 2 compounds, are they the same? Are they enantiomers? Are they diastereomers? Constitutional isomers or not isomeric? So if something's not isomeric, what does that mean? So it's not isomeric. That means they don't have the same molecular formula, right? At the end of the day, these isomers all have the same molecular formula, right? So if all of a sudden you see something that, right, if one has 2 oxygens and the other one has 3, those aren't isomeric at all. Those are just completely different compounds. Right? They're not isomers. So isomers, remember, have the same molecular formula, right? So let's say so the sampling question, we have CL, F, another CL, have another F. Okay, and so it's asking us, are these the same compounds? Are they enantiomers? So same compounds is kind of self, you should know what that means. Same. I don't know why I drew that circle. But doesn't want to go away now. Okay. Yep. Same. Enantiomers. So if they're enantiomers, that means they're absolutely everything's opposite, right? If something's R in one, it has to be S in the other, right? All their stereoceners are the same, so or different or opposite. So that would be mirrors, mirror images. They could be diastereomers. Diastereomers, how many stereoceners must you have to have diastereomers at least? You must have at least two asymmetric centers. And at least one's the same, at least one's different. With one different. So we're comparing two molecules to each other, right? We're always comparing two molecules here, right? The question here is not asking, is this molecule chiral, right? It's not asking us that, right? We're asking comparing, what's the relationship between these two things? So they can be diastereomers and enantiomers, same.
And you can never have a diastereomer that's an enantiomer?
So a pair of diastereomers is different than a pair of enantiomers. Enantiomers are mirror images, every stereocenter is opposite. Diastereomers, at least one's the same, and at least another one's different. And diastereomers have different physical properties. And then the last one here is constitutional, which would just mean, right, different bonds, right? Same molecular formula, but different bonds, right? So this is easy, right? So are these isomers of each other? They have the same molecular formula? Yeah, so they are isomers. Are they constitutional isomers? Right? So they're not because, right, this chlorine and this chlorine and this fluorine are, right, a bond away from each other, right? They're 1, 2 to each other. If the fluorine was over here, F was over here, then they'd be constitutional isomers, right? They'd be bonded to different things, different bonds. So there's not constitutional, so we can cross that off. They are isomers. Are they the same? Are they enantiomers or the diastereomers? Well, to be a diastereomer, you need to have how many stereocenters? At least 2. Does this have 2 stereocenters? It does, right? There are, right? There's an asymmetric center there, right? So each of them have 2. So diastereomers are possible. That doesn't mean these are diastereomers, but they're possible, right? So, but if you only have one stereocenter, if you only have one asymmetric center, can you have diastereomers? No. So, right, that's an easy one you should be looking for, right? Di, as in at least a 2, right? So if you only have one asymmetric center, you know it can't be a diastereomer. Not the case here, though. Too bad. So these could still be diastereomers. We haven't eliminated that possibility yet. They could be exactly the same. They could be enantiomers, in which case, right, that means if this was R, that would have to be, they're enantiomers. If this is R, this has to be, if they're enantiomers, this is R, this would have to be S. And if this is R, this would have to be S, right? They would be opposite. I'm not saying that's what they are, right? So there's 2 ways to approach this. Some people can look at this and know the answer. And if you can do that, and then if you want to convince yourself, there's another way to reconvince yourself. So give me some options on what to do here. So we have,
Look at the chairs.
you could look at the chairs and say what?
They're opposite.
They're opposite. So you can just look at it and you can say, some people can look at this and say, it's like 2 things, it's like my right hand and my left hand looking at each other. These are enantiomers. They are enantiomers. Some people can't see that. That's fine. Well, if you can't see that right away, what would you need to do?
Prioritize the different centers.
Prioritize the groups and find out, is this R, is this S? Right? So let's do that. I'm going to draw in, right, to help us draw in the H's. Right? So let's rank these. So let's go to this one. Right? That carbon, what's the highest rank thing? Cl. So we'll call that 1 red. Should I do red or should I do 1? Should I do colors or numbers? Colors? I'll do colors. Red. What is lowest priority? H, so that is green. I think. It's kind of green. Green. Now, how do we rank these other ones? What's this one going to be? White or blue? Which one has higher priority? This way or this way? The first way. Good. Nice. Good answer. I think this way or this way? The first way. Red, white. So that'd be white, and this would be blue. Okay? Now, so what is that going to be then? So try and make your model. And you can kind of think about this coming out at you, and this kind of going away. Right? It's a three-dimensional chair structure. This is coming out. This is going away. So which model does it match up to? I think it's R. This is a good time if you need to pause this, you pause this and do it yourself. So it's R.
Can you see that yourself?
Yes. I can. But I'm old and I've done this a long time. What are we doing here? What's green? Red. What's going up? Is up white or blue? White. This way is blue. So what is this one? This is S. Good. All right. Again, if you need to use your models, by all means, use them. Right. These chairs are a little difficult to see. This would be coming out at you. This would be going away. These two are in the plane. You could do it that way. So R and S. So what is this one going to be? Same ranking, so it's still R, green, white, blue. What do we got here? I think it's S. So it's S. So we know right away they're not the same then, right? We know that now, so we can cross that out. Now the one below, if we do the priority rankings, we'd have green, have red, white, blue, and this one should be R. Right, so we did the priorities, and this makes sense. So if this is R, this one had to be S. If these are enantiomers, if this is R, this one should be S. This is S, this should be R. So everything should be opposite. So these are not diastereomers; they are enantiomers. If they were diastereomers, right? What would it be if they were diastereomers? But what would they have? I mean, just letter-wise. If this was RS, what's the diastereomer for RS? SS. Or RR would be a diastereomer to this one, right? Good. Blake, what's your question, bud?
Huh?
What's your question?
That was it.
That was it. That's right. So everybody see that? It makes sense that if one of these, if this was S and this was S, these would be diastereomers to each other, right? One's the same and at least one's different, are diastereomers. Everything's opposite, they're enantiomers. Right. Let's do a question that asks from Sapling, what is a stereocenter? Stereocenters, question mark. So they can be divided into two categories. The one we know is our asymmetric centers, sp3, bonded to 4 different things. Right? So all asymmetric centers are stereocenters. But all stereocenters are not asymmetric centers. All asymmetric centers are stereocenters, but all stereocenters are not asymmetric centers.
And is it true that all asymmetric centers have to be carbon?
No.
Okay.
For as far as mostly as no.
Okay, because I got confused on this one.
So stereocenters are different. Right?
So you're talking about asymmetric centers?
I'm talking about asymmetric centers right now. sp3 hybridized 4 different things. Notice how I didn't just say carbon. I said sp3 hybridized 4 different things. Because there might be some questions in Sapling that also involve, right, something like a nitrogen with stuff on it. Right? Has a plus charge and say it's this. Right, that's nitrogen with 4 different things on it. What's the hybridization state of that nitrogen? Yeah, it has no pi bonds, it's sp3 hybridized. Does it have 4 different things on it?
Yeah.
Is it an asymmetric center? Oh yeah. Okay. Good, we hit that too. The other type of asymmetric centers are the EZ. Right, so if you're double bond, your alkene can be E or Z. Both of those things in that pi bond are stereocenters.
They're not asymmetric.
They're not asymmetric, but they're stereocenters. But both, it's either 2 of them or none of them, right? So can all alkenes be E or Z? All alkenes are not E or Z. But if it is E or Z, then both pieces across that pi bond are stereocenters. So that's a stereocenter, and that's a stereocenter. The reason why it's a stereocenter is because if you switched places, right? Right now, this is what? This is E or Z? E. If I move this methyl to here, if I switch the methyl and the H, do I change from E to Z? I do, right? So that's why these are stereocenters. So it's either an all or nothing. If your alkene can be E or Z, then the pieces in the alkene are stereocenters, right? But if it can be E or Z, then neither of them are. Either all or nothing. So let's look at some examples from this problem. So now in this case, it asks you a couple of things. I think it asks you to highlight the asymmetric centers. So asymmetric centers mean sp3 hybridized 4 different things. So how many asymmetric centers are there here? 1. And where is it?
One attached to the chlorine.
The carbon attached to the chlorine. That's the asymmetric center. Is that also a stereocenter?
Yes.
Yes, it is. Okay, good. So now you want to look. Now it's going to ask you how many stereocenters do you have? Right. Well, we already know we have 1 because we have the asymmetric center. But now it's also going to ask you about what's going on with this double bond, this alkene. Can this alkene, I know it's a nitrogen, still an alkene, still a pi bond, right? Can that be E or Z? So that's what we have to think, okay, well, maybe not. Well, I know H and carbon are different, so this side's good. I can prioritize here, right? So the question is, can you prioritize? Carbon, carbon, tied. Carbon bond to carbon. Carbon bond to chlorine. Is this side higher ranked? Yes. So can this be E or Z? Yes. So that means these guys, both this carbon and this nitrogen, they're not asymmetric centers, but they are stereocenters, right? They're those geometric, right? If I labeled these, remember these geometric isomers are EZ isomers, right? I wrote that down, I think, on the board. E/Z, right? If you can be E or Z, you're a geometric isomer, right? But you're also a stereocenter. All right, so this one has 3 stereocenters, and one of those stereocenters is an asymmetric center. It also asks you, is this molecule chiral or achiral? Well, usually when you have an asymmetric center, you are chiral, right? So if it has an asymmetric center, most of the time it's chiral. Who knows an example of having asymmetric centers but yet still being achiral? Meso compounds, right? So let's just layer this in. A meso compound, right? What's a meso compound? A meso compound is a compound with asymmetric centers that is achiral. Right? It's achiral because it has its own internal mirror plane, right? Not like enantiomers. Enantiomers are mirror images of each other, a mirror between 2 things, right? Like Snow White. Huh? Right? No? I haven't seen that movie. Well, yeah, I have. I should pause this. Yeah, I just forget about the whole Snow White thing. Take that back. That analogy is not going to work. But it's not going to work yet. I haven't figured it out yet, but it'll probably never work. So enantiomers have the mirror images of each other, right? Enantiomers are like looking in the mirror at yourself. A meso compound has asymmetric centers, sp3 hybridized, 4 different things bonded to it, but it has an internal mirror plane. Internal, right? You can cut this molecule in half, and it looks like it's a mirror image of itself inside itself. Internal mirror plane has an internal mirror plane. That's meso. So that's a compound with chiral centers, with asymmetric centers. That's achiral. Has asymmetric centers, but it's achiral. Most of the time, if you have an asymmetric center, you are chiral, right? Most of the time. The classic meso example is ourselves, right? We are meso. We have asymmetric centers. Our hands, right, are enantiomers of each other. Our ears, our feet. But do we have an internal mirror plane? More or less, right? Yes. Humor me, right? We have an internal mirror plane. So we're meso. We have asymmetric centers, but we're meso, right? We're achiral. Okay. Good. The other part of this one was basically getting into the heart of this discussion about these geometric isomers, these EZ, and how do you identify stereocenters there? So you have 3 alkenes, so it's a triene, right? We can name this even if we wanted to. We can name this as a triene. 1, 2, 3, 4, 5, 6. So it's a hexene. And we number, which way should we number? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6? Left to right or right to left?
Left to right.
I like left to right. Because 1, 2, 3 versus 1, 2, 3. 1, 2, 3. But this methyl would have a lower number going this way. Right? The methyl could have a lower number going this way. So, you have 3 alkenes. How many of these alkenes can be E or Z? Which one? Which alkenes can be E or Z? Just the middle one. Right? So how many stereocenters do you have then?
2.
Has to be 2 always, right? It's all or nothing. Right? If this alkene can be E or Z, then they're both stereocenters. If the alkene can be E or Z, then none of the pieces of the double bond are stereocenters. Right? I know this has 2 H's. Right? So this alkene can't be E or Z. It doesn't matter this is bonded to a carbon that's an H. If it can't be E or Z, neither part is a stereocenter. So this one just has 2 stereocenters. Is it chiral or achiral? So chiral things usually have asymmetric centers unless they're meso. Does this one have an asymmetric center? No. So you think it's chiral or achiral? It's achiral. Good. Look at so I have a pre-drawn molecule here. So the first step in naming this is we need to find the parent chain. So we need to find the longest chain of carbons with the alkenes in them.
Is there naming on this one?
We did naming.
Okay.
Yep.
What we're naming stuff?
What? So the first thing I like to do when I do these is I like to circle the longest chain. All right? There is the longest chain. I hope you can see that. It didn't matter if I went with this or this, right? Because these two are actually the same. So I went there. Longest chain with the double bonds in it. All right. Next step, we need to figure out how long is our chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Decene. Right? Decene. Well, we have two double bonds, so it's a decadiene. Right? It's a decadiene. Right? That's our root parent name. That's the thing we put the farthest to the right. A decadiene.
What if it was 3?
It'd be a triene.
Tridecadiene?
Decatriene. Decatriene.
Wait.
Decadiene.
Is there a reason it's not decadiene? Oh.
Decadiene.
Yep.
There's 2. There's 2 alkenes, so it has to be a di-2-ene.
Oh, okay.
Di? Alright? So now we got to figure out the numbering, right? We want to number such that the lowest, we can put the first, we want to have the lowest number possible for our alkenes. So which way should we number? Should we number this way or this way?
From the first way.
First, this way?
Yep.
No.
No.
From the right.
This way.
Right.
Right. 1. That way this one alkene could be 1. 2. You want to have the lowest one possible. It's not a totality thing.
The lowest which one?
Wherever the lowest you can start at. Like,
The lowest you can start at is what you want to do. You always want the lowest you can start at.
the other way.
The other way would be 1, 2, 3.
Oh.
Oh, but we're doing the alkenes now.
Yeah, I was looking
All we
at
care about is the
I was
alkenes.
like, what?
All we care about is the alkenes.
Okay.
Right? Okay, so now we have the first, we have a 1, 7. Right? We'd write in 1, 7 decadiene. The 1, 7 telling us, right, where the pi bonds are at, what carbon they start on. Good. What other pieces do we have here? We have a what one?
2 ethyls and
We have 2 ethyls, so we'd say, oh, we have a, where in what carbon? We have a diethyl. And where are 6N, 6,8 diethyl? That's one piece. What else are we missing? A 4 methyl. Good. And now we need to go back and check. So now we got to put these together. And what comes first? Diethyl or methyl?
Diethyl.
Nope.
Di.
Di and tri don't count for alphabet.
Oh, yeah. It's still
Well,
first.
that's
It's still
fine, man.
But E is still before M. So yes, diethyl is first. But not for the reasons you thought. So it'd be 6,8 diethyl, 4 methyl, 1, 7 decadiene. But are we done?
Yes.
Nope.
We need to name it.
Apparently not. Right? So which alkene, can we name these alkenes E or Z? Can we name this alkene E or Z? No, because it's 2 H's. What about this one?
Yes.
Yes, we got to prioritize that. So we cut this guy down the middle. We look at that carbon and we say carbon to carbon. Oh, wait a second. Carbon to carbon, tied.
Yeah, you can't.
Carbon, carbon, tied. H, 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 H. Going out.
Oh.
You can't do it. Can't do it. That's an ethyl, that's an ethyl. Can this alkene be E or Z? No. Are we done? We are done. All right, so 6,8 diethyl, 4 methyl, 1, 7 decadiene is the answer. Right? So be careful with that, right? Be careful, right? So you see, I know you've seen these with H's, but now look at I pulled a trick. Right? So another sapling kind of question. So remember our Fisher projections. Right? Our Fisher projections.
Shut up.
How do we visualize this? Right? So there's no wedges and hatches yet. Remember Fisher projections, they're a little different. So the horizontal things are wedges and the vertical things are dashes. So that's the three-dimensional picture that even though it was flat like a plus sign, this is what they're implying. You should look at the flat thing and say, oh, it's this.
Is there some saying, like something about a
Oh.
stepmother hugging you or something? Or somebody was telling me how to remember that. Like the horizontal, I don't remember.
Haven't heard that one.
It
It
says
sounds about as good as my Snow White mirror on the wall thing, though. Right? So next thing we have to do, right, is, but you can think of a stepmother hugging you, I guess, here. If that works.
Like she's coming at you.
Like she's coming at you,
Yeah,
like,
and then she's going backwards. So it's
yeah,
like-
okay. So should we prioritize these things? So that's the next thing we have to do is rank these. So what is the highest ranked thing? So that's red. Lowest ranked thing is? So that's green. CH3 is going to be red, white, or is it white or blue? Blue. And this is white. Let's see what we got.
Right?
Yeah. I love naming. So this one, if we look at this, hopefully you map this and you should have came up with R. R,